Sample problem 23.02. Plug through the closed Gaussian cube. A non-uniform electric field given by E 3xi plus 4j pierces the Gaussian cube shown in the figure 23-7a, the one on the right. E is in newtons per coulomb and x is in meters. So question is, what is electric flux through the right phase, the left phase, and the top phase? We consider the other phases in another sample problem. Actually, that problem is, what is the net charge enclosed by the Gaussian cube of sample problem 2302? So now let's take a look at the picture. So the electric field already exists in the space that pointing in right upward, as you can see here. So that electric field can be decomposed into x component in the x-axis, the one in the y-axis. So that electric field passing through this Gaussian cube, like this, and you can actually calculate the quantity of electric flux by integrating the electric field times area vector on x, y, z phases. In order to start estimate the quantity of electric flux, first step might be to set up the area vector. Normally, area vector is defined by the vector is perpendicular to the surface of Gaussian cube or Gaussian surface. So here, A vector A is the area vector, and that is normally perpendicular to Gaussian. It's Gaussian surface. So if you look at the picture B, that the arrow indicates the direction of the area vector on the faces of this Gaussian cube. So there's three faces, the 6 faces. So there are 6 different vectors aligned in the x, y, z axes. So if you look at small area segment on the face, then that area segments could be defined by dA, that is area element, which is small fraction of this base of Gaussian surfaces. So that is the area vector element, area vector element. And this dA vector could be defined by unit vector. So the question is we have to find the flux of electric field on the right face, which is aligned with the x-axis. So dA, in that case, the dA vector, the area vector element, is expressed with the scalar quantity of the area vector times unit vector I. So I vector is on the x-axis. So this dA vector, the face area vector, is aligned in the positive x-axis. So using that area vector, we can estimate the flux density and the flux of electric field along the right face of this Gaussian surfaces. So for the a surface on the positive x-axis, is given by this definition that the flux element is expressed with the d pi r. That is the electric field out of this vector quantity of field on that spot pointing the right upward times area vector dA. So that is the flux quantity passing through the small area of dA on that phase. So now next step is to estimate total flux out of that surface. So that is integral of, so let me rewrite it. So that flux, electric flux out of right phase is integral of d IR. Then that you replace that with the electric field expression, then that integral of electric field dot product dA. Now let's replace electric field and the area vector with their given condition. So that is integral of the 3xi plus 4j dot product dAi. So that vectorial expressions can be converted into dot product of normal vectors. So that is integral of dx times dA first, and times I vector dot product I vector plus integral of the 4 dA times I cross product and dot product j. So as you know, the I, j, k are the normal to each other, which means their unit vectors are perpendicular to each other. In the case of the dot products between the two vectors on normal direction lead to the zero vector, so that I dot product of j should be equal to 0. So only leave this one. And the dot product of unit vector itself, that should be equals 1. So this lead to that the answer of integral of 3x dA. So as you can see, 3x is constant value that could be out of integral, because the x in this phase of this cube, x is the 3 meter everywhere. So x value usually is not varying over surface. So that can be out of the integral. So if you take that into account, then 3x could be out of integral, then you have dA. So that is area of this face of this Gaussian cube. So that this one is area of the right face of this Gaussian cube, which is this one side of this cube is 2 meter. So total area of this face is 4 meter square. So you multiply, then you got to times 3 meter times integral of that is 4 meter square. Then that is 36 36 Newton meter square over C. Okay, that is flux of the that phase of the Gaussian surfaces, the Gaussian cube. And now with that idea, let's just estimate the flux on the left side, the left face and the top face too. So for For the left phase, everything is same, pretty much the same procedure you need to take, but the some of the variable like x should be different. So here in the left phase, x, as you already saw, that is 1 meter. And also dA should be defined with the negative direction, so that should be minus dA I. Now you want to just do the same estimate. So the flux on the left phase is integral of electric field dot product of dA. So if you plug all those expression of electric field and area vector, then that should be minus 3x integral dA. So here, this one is again is 4 meter squared, and the x is 1 meter this time. So that is minus 12 Newton meter squared per coulomb. Now let's just estimate the flux on the top phase. So top phase, now in top phase like this, right? And then that is pointing upward. So area vector dA point upward, so that dA could be expressed with their magnitude of area vector times j, unit vector. So with that quantity, the flux on the top face could be expressed with the integral of 3xi plus 4j dot product dAj. So that is integral of 3x I dot product j plus integral, oh, here's the dA too, integral of the 4 dA j dot product j. So this I product j equals 0, and j product j is equal to 1. So that only leave 4 integral of 4 dA. So the 4 could be out of integral as is that's just number. So here integral of dA is the area of top surface, which is still 4 meter square. So total flux out of that surface, the face of that Gaussian cube is 16 Newton meter square over coulomb. Second question is, what is the net charge enclosed by the Gaussian cube of sample problem 3.02? So based on the Gauss law, the net charge inside enclosed Gaussian cube or Gaussian surfaces could be given by the total integral of electric field over the total surface of Gaussian cube. So in this case, we have to first estimate electric field integrated by the surface area or face of size of the Gaussian cube first. That should be equivalent to a total charge inside of this Gaussian cube. So we already estimate the flux of 3 surfaces, left, right, top, and the next one, then we should actually come up with the numbers of electric field, total electric field times surface area, and on the other 3 actually faces. So for the bottom face, next step, for bottom face, the bottom face is which is the on the negative y-axis, and the area vector is then should be minus dA j in the y-axis. So if you plug that into total flux across or through that, the bottom face is integral of electric field dot dA. From that, that should be minus 3xi and then j 4j dA j, right? So from that, just like the electric field flux on top surface, total amount of actually the flux should be same as the one on the top face, but with a negative sign. So that should be 16 Newton meter square per coulomb. Then the remaining faces on this Gaussian cube is the front and back faces, front or back sides. So we can define first area vectors out of those two faces. So for front and back faces, the area vector element is given by this definition in positive g-axis. That should be the AK, negative basis, and that should be minus the AK. But as you know, dot product of two normal vector is equal to 0. So that leads to the flux through those two faces out of electric field and area vector must be 0 out of these two normal vector dot products. So from that, total net flux through 6 faces of or 6 sides of this Gaussian cube should be given by 6 numbers, 36 Newton per Newton meter per Newton meter square per cube per coulomb, and minus 12 plus 16 minus 16 plus 0 plus 0 Newton meter square per coulomb. So this is that is right, this is the left, this is top, this is bottom, and this one is front, this one is back. So all 6 sides of this cube is calculated based on the definition of the flux, electric flux. So from that, total flux out of this Gaussian cube surface is 24 Newton meter square per coulomb. Now we have to apply the Gauss law to estimate net quantity of the net charge inside of this Gaussian cube. So that is basically electric permittivity times flux is same as net charge inside of this Gaussian cube. So you have to multiply the net, and C is epsilon 8.85 times 10 to the minus 12 coulomb squared per Newton per meter square, and you have the total flux is 24 Newton meter squared per coulomb. From that, net charge inside of this Gaussian cube should be 2.1 times 10 to the minus 10 coulomb.